Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about conductors which are at equilibrium and yet in an electric field. This video is kind of the wrap-up, I guess, of the series on electrostatics, specifically with regard to forces and Coulomb's law in electric fields. And we've kind of gone through Coulomb's law. We've kind of described what electric fields are, what they do. We've discussed Gauss's law and how we can maybe apply it to a few scenarios. We've even discussed electric field lines. So let's turn now to one of the interesting sort of implications of all of this. Okay, so we have an electric field, let us say. Maybe it is a field that is generated by a set of charges somewhere. Maybe the field just happens to be something like this, where it's a uniform field. Now we place inside of that field a conducting object. Maybe it's just oblong shaped like this. And this field, with the object not present, would be represented by these black lines. Now inside this object, since it's a conductor, are charges that can be sort of like freely arranged within the conduction bands. Essentially, if I have an electron hole or an electron, that can move about according to any forces that may be exerted on it. So this hole would be accelerated this way, and this electron would be accelerated that way. And so the end result of this is that this field will sort of rearrange the charges within the conductor in such a way that we end up with, let's say, all of our minus charges kind of lined up over here somewhere, and then all of our plus charges separated over to here somewhere. And that in turn basically means that we're going to have rearranged these field lines somewhat because of the presence or absence of these charges. So the field line out here continues as if there was no conductor present, and then here it terminates on a negative charge. And again, we have our field line out here, and here it terminates on our negative charge. We've got our field line down here, and right here it terminates on a negative charge. And then this positive charge must be the source of a field line, as must be this positive charge, as must be this positive charge. And so essentially I end up with a situation that looks like this, where I have more or less the same field as I had originally outside of the conductor, but inside of the conductor I end up with E equals 0. So all of my lines that enter terminate pretty much immediately on the surface. All of the lines that leave originate again on sort of the opposite surface or on another surface. So this is the basic way of analyzing these conductors in an electric field problems, namely that inside of a conductor at equilibrium you have a field of 0. So inside the conducting material, and of course we're assuming that everything is at equilibrium, the electric field is 0. And then at the surface, the E field is parallel to the local area vector. That means that it is perpendicular to the surface. Okay, so those are the basic conditions. The last sort of condition here, or the last implication, is that the charges within the conducting material will tend to rearrange themselves to make these two conditions happen. And if you look at the picture again, you can see that the charges are all at the surface. So we could say free charges in conductor are at the surface, or at the surfaces of the conductor. And again, that is actually just a condition of equilibrium for the conductor. So there's E equals 0, but also there's no charges located inside the bulk of the conductor. So let's consider a few implications of these statements. Let's take, for example, a spherical shell. So in cross-section, the spherical shell might look like this. So I've got some spherical shell here. This is, we'll label it as spherical shell of conducting material. And let's say that we place inside of this spherical shell a single charge, point charge. We'll make it like we can make it plus or minus, I don't care. We'll make it plus. Now we draw for ourselves the field lines that go with this charge. Well, according to the rules that we have for field lines, you should have field lines radiating outward from this charge, like so. Now we get to the surface of the conductor. Let's say that this point charge represents a total, even though I usually use little q for point charge, I'm going to use a big Q in this case. Well, these field lines have sort of hit the surface material of the conductor, and they have to be somehow terminated. Okay, so how do you terminate these field lines? Well, the answer is that we need to put some minus charges on this interior surface of the shell in order for these field lines to all terminate. How much minus charge, you may be wondering? Well, I have to have a termination point for each line that originates. So according to the field lines rules, this surface has charge of negative Q. Well, if this shell was originally neutrally charged, then the fact that I've pulled minus Q worth to the inside means that those have to leave holes somewhere. And the holes, as it turns out, are out here. So that would be these plus charges out here, which are kind of left behind the holes. And those plus charges, in turn, must each generate a set of field lines, which may look like this. Oops, I don't have my field line color chosen though. So we get a field line here, we get a field line here, get a field line here, get a field line down here, get a field line down here, get a field line down here, get a field line here, get a field line here. So basically I have E equals 0 inside the conducting material again, so this little shell. And then on the very inside, the hollow area, this E field should look like basically K, or Coulomb's constant K, times the charge Q divided by the R distance, essentially, from a field. So this, if this right here represents radius R, and we want to know what is the E field value at this point right here, then that would be given by your equation here. Now, we'll call this like R inner. What would happen if we wanted to find the field at, say, this point right here? So this point right here exists on an even larger sphere, we'll say that the radius to this even larger sphere is, we'll call it R outer or R outside, something like that. Well, it turns out that from Gauss's law, the E field for out here, E out, looks like KCQ over R outer squared. So I have R inner squared, I have R outer squared. Basically, this entire field looks the same as a field generated by a point charge at the center of the sphere, except for we have sort of an interruption in this region where the actual material is. Let's do another example. Again, let's say that I have a sphere of conducting material. And again, we'll draw it in cross-section here. And again, let's say that I happen to have a total charge on this sphere of Q. So we'll do a big Q for our total charge. Where must the charges be arranged? Okay, well, pick a Gaussian surface inside of this hollowed out area. And this Gaussian surface inside this hollowed area has a total Q enclosed of 0. Oops. It doesn't matter how big or how small I make this, as long as it's inside the hollow area, I do have a total of 0 enclosed charge. And in fact, that remains true even if I choose my sphere or whatever surface to be here, or here, or even here. All of these end up with 0 enclosed charge. And the conclusion to that is that because I can pick sort of a random shape and sized object within this region, and all these random shape and sized objects end up with 0 enclosed charge, it follows that the E field in this region is 0. We already knew that E was 0 inside of this part of the conducting material. So where are all the charges? Well, they're basically just arranged here on the outside of my conducting sphere, the outer surface, like so. So if that's the case, we might ask, therefore, what does the field look like? Well, the field lines must originate on our positive charges and go essentially until they hit a negative charge or go infinitely far away. And so my field arrangement ends up looking basically like this. Now I'm again going to choose a Gaussian surface, but this time I'm going to label it in orange just so it doesn't get cluttered with all these purple surfaces. So my Gaussian surface in this case is this nice orange sphere, which I'm going to draw like this. Well, for this one, my flux phi E should look like Q enclosed, which is capital Q, divided by epsilon naught. That is E dotted with A. And so that means that E must be Q over epsilon naught times area. Now the area of a sphere is 4 pi r squared. So I end up with this E, which is the same again as a field by a point charge located at the center. So that's it. That's all for today's video. I hope that you have enjoyed it, and thanks for watching.